Today we'll be starting off with Unit 2 of Design Analysis of Machine Learning Algorithms. Cross-validation in machine learning, it is a cornerstone for machine learning experiments. It ensures that our models are not just good at memorizing data, but are capable of generalizing to unseen data. A formal definition would be cross-validation is a technique used to train and evaluate our model on a portion of our database before reporting our dataset and evaluating on new portions. It is a resampling technique used to evaluate the performance of a machine learning model by dividing the dataset into training and testing subsets multiple times. Now we're going to study the need for cross-validation. One of the uses is to efficiently use limited data. In small datasets, splitting data into separate training and testing sets can waste valuable information. So cross-validation in this case allows the entire dataset to be used for training and testing at different points, maximizing data usage. Like for example, for a dataset with only 100 samples, a simple train test split leaves only 20 samples for evaluation. Using 5-fold cross-validation, it ensures all 100 samples contribute to both testing and training. While choosing machine learning models, we need to compare different models to see how each model performs on the given data set. Another use case would be to prevent overfitting. When a model learns noise or irrelevant details in a training data, it may perform poorly on the new data. So cross-validation ensures that the model is tested on multiple subsets of the data, reducing the likelihood of overfitting. For example, polynomial regression model might perfectly fit on the training data but might fail on test data. Cross-validation is used to evaluate how well the model performs on unseen subsets. Another example could be to evaluate the model stability. In this case, cross-validation measures the model's performance across multiple data splits and provides insights into its consistency and reliability. A stable model performs similarly across all folds, indicating the robustness. Okay, the steps involved in cross-validation are: the step 1 is first we split the dataset. We divide the dataset into k subsets in which each fold should have approximately the same size. For example, for a dataset with 1000 samples and 5-fold cross-validation, we divide the data into 5 equal subsets, each containing 200 samples. Next, we select one fold as the test set and we choose one of the k folds to act as a test set, and the remaining k-1 folds are used for training the model. Like for example, in the first iteration of a 5-fold cross-validation, the fold 1 will have the test set which has 200 samples, and fold 2 to 5 will have the training set which has 800 samples. Step 3 will be training the model on the training set using the k-1 folds to fit the model. The model learns patterns, relationships, or parameters based on the training data. Step 4 would be to test the model on the test set. We use a test set to evaluate the test model and compute performance metrics such as accuracy, precision, recall, F1 score, or mean square error. And then we get the actual average of all these measures. This average is equal to the total model performance. And the last step would be repetition of all the k folds so that we train and test the model k times the different fold used as a test set in each iteration. For example, for the cross 5 cross validation, test on fold 1 and train on folds 2 to 5 is done in iteration 1. In iteration 2, test is done on fold 2, where the training is done on folds 1 and 3 to 5. And this is continued until each fold has been used as the test set once. Now we're moving on to types of cross-validation, discussing about the types of cross-validation. In general, there are 7 different types of cross-validation techniques. Here we'll be discussing about the 3 main ones. That is the leave one out cross-validation, the k-fold cross-validation, the stratified k-fold cross-validation. Now leave one out cross-validation, we treat each data point as a test set, while the remaining n-1 data points are used for training. Suppose we consider a data set with n points. n-1 points will be used for training and 1 point will be used as a testing set. Now the entire data set is used for training, and that one singular data point is used for testing the data. After the 1 point is done with testing, we move on to the next point, that is another point is chosen as a testing data, and the rest of the points will be used for training, and this process will be repeated for the rest of the data set, that is n times. Then we calculate the average performance metric across all iterations. A few advantages of this technique is minimal bias, as all data points are used for testing and training, and it is also suitable for small data sets where using every data point is essential. But one major drawback of this is it can be computationally expensive for large data sets, as the model has to train n times. So moving on to the next one. The next one is k-fold cross-validation technique. In this, we split the data set into k equally sized folds, where we use k-1 folds for training and the remaining for testing. And in this, we repeat the process k times with each fold serving as the test set once, in which the final performance measure will be the average of the output measures for all the 5, that is in this case all k iterations. Few advantages of this are it is efficient use of data, as every data point is used for training and testing, and it is also suitable for both small and large data sets, unlike your leave one out cross-validation technique. But again, like your LWOCV, this also is computationally expensive for large data sets if the value of k is very high. Next is the stratified k-fold cross-validation. This is similar to your k-fold cross-validation, but here it ensures that each fold maintains the same proportion of target classes as the original data set, and this is particularly used for imbalanced data sets. Now, in the normal cross-validation, the data is divided without keeping in mind the distribution of individual classes. Hence, the model cannot properly predict for minority classes. This problem is avoided in stratified k-fold cross-validation. Hence, it provides more reliable results for classification problems with skewed class distributions. For example, consider a binary classification data set with 70% positive and 30% negative labels. Each fold of the stratified k-fold will also have a 70-30 split, ensuring that it has consistent evaluation. Bootstrapping. Bootstrapping is a sampling technique used to estimate the performance of a machine learning model or a statistical measure by generating multiple datasets through random sampling with replacement. Now, the purpose of bootstrapping, now it is to evaluate the model performance when the dataset is small, and it is also used to estimate the variability of a model's predictions or statistical metrics like mean, or it can be a variance as well. The key idea is instead of dividing the data into fixed training and testing subsets like your cross validation, now bootstrapping repeatedly samples from the original data set to create multiple data sets for training and testing. Now, when it is used, it can be used in small data sets to maximize data utilization. You can also use it to evaluate reliability of model predictions or statistical estimates, and it is also used to assess the variability of the model's prediction, that is the bias and variance trade-off. Now, steps involved in bootstrapping are: we start with the original data set. In this example, we have the 100 samples. Assume that the data has 100 samples in this case. We generate the bootstrap samples. We randomly sample n data points with a replacement from the original data set. In this case, sampling with a replacement means the same data point can appear multiple times in a single data set. For example, now the original data set here, we have 1, 2, 3 up till 100, which is divided into 70 samples, where in one sample we have 4 that is repeated twice, and 4 appears in all the other 3 other samples as well. The next step is to train the model on the bootstrap samples. We use each bootstrap sample as a training set to build the model, and the remaining data points, which is known as the out of bag samples, are used for testing. And then we evaluate the model. We test the model on the OOB samples and record the performance metric, that is the accuracy, the mean squared error, and etc. Based on that, we calculate the average performance metric across all iterations to estimate the model's overall performance. And optionally, we can compute confidence intervals for performance metrics as well. Like for example, for 100 bootstrap iterations, if the average scores are 85%, 87%, 88%, etc., the average accuracy is the sum of all accuracies divided by the number of iterations. Now, a few examples and few advantages of it. It can be used for efficient use of data. Then it provides confidence intervals for performance metrics, and it does not require assumptions about the underlying data distribution. Now, some use cases of bootstrapping is predicting house prices. Let's say we take the original data set of n equal to 100 house records with features like size, location, and price. We create 1000 bootstrap samples by random sampling. Then we train a regression model on each sample, evaluate each model on the OOB samples, and then calculate the mean accuracy and confidence intervals for the final evaluation. To random forest algorithm. It is a versatile and ensemble machine learning algorithm that combines multiple decision trees to make predictions. Random forest can be used for both classification and regression tasks. Now, where does the idea come from? The key idea of random forest is to create a forest of decision trees during training and aggregate the results to make a final prediction. Random forest introduces randomness by using bootstrap sampling and feature randomness to reduce overfitting and can to help improve generalization. Now, how does it work? A random forest first creates bootstrap samples by randomly selecting subsets of dataset with replacement, and each subset is used to train a single decision tree. Then for each bootstrap sample, we grow a decision tree. At each split in the tree, we select a random subset of features and split the data based on the best feature from this subset. Once all the decision trees are trained, the algorithm makes prediction. Either the classification, for example, we use a majority vote across all trees, and in regression, we take the average of all tree predictions. Now, few advantages of random forest is it reduces overfitting, where it combines prediction from multiple trees, making it less likely to overfit compared to a single decision tree. And it handles high dimensional data. It works well with data sets with many features thanks to random feature selection. It also has robust to noise versatility, which means it is suitable for both classification and regression problems. It also provides a ranking of feature importance, which helps in feature selection. Key parameters in random forests could be the number of trees, the maximum depth of each tree, the number of features considered for splitting at each node, and we also take into account the minimum number of samples required to split a node, controlling the tree growth. Test. It is a statistical hypothesis test used to determine whether there's a significant difference between the mean of two groups or samples. In machine learning, it is often used to compare the performance of two models or algorithms. T-test is generally of two types. One is the independent t-test, also known as the two-sample t-test. In this, it compares the means of two independent groups. For example, comparing the performance of model A with model B. And second is the pair t-test. Here it compares the means of two same groups under two different conditions. Here, for example, we are comparing model A's performance before and after hyperparameter tuning. Now we will go through the steps to calculate the t-test. If you want to compare the performance of a model A and model B based on the accuracy scores from a 10-fold cross validation, the first test will be we have to formulate the hypothesis, where there are two types of hypothesis. One is the null hypothesis. In this, there is no significant difference between the means of both model A and B. And the alternative hypothesis is there is a significant difference between the means of model A and B. Secondly, we'll collect the means of two data. We use the accuracy scores obtained from 10-fold cross validation for both models, and we calculate the accuracy. We calculate the average accuracy, where it is equal to the sum of accuracies of model A divided by the number of folds. Now we compute the same for model B as well. The next step is to calculate the standard deviations for both set of scores using a given formula. After that, we perform the independent t-test using the test in function from the SciPy stats library to perform the t-test. And we also calculate the degrees of freedom using the formula. df is equal to na plus nb minus 2. Alternatively, we also find the p-value using the SciPy stats library. And then finally, we interpret the results and assume the t-statistic and p-value. Here the t-statistic measures the size difference relative to the variation in the sample data, and the p-value indicates the probability of observing the results given that the null hypothesis is true. So in short, the t steps are: we formulate the hypothesis, we collect the data, calculate the mean and standard deviation, compute the t-statistic, we find the p-value using the library, compare the p-value with significance level, and then interpret all the results. Brief detailed explanation of McNemar's test. McNemar's test is a non-parametric statistical test used to compare performance of two classifiers on same data set. It evaluates whether there is a significant difference between the prediction of two models in terms of binary outcomes. The purpose of this test is to check if the two models have different error rates using paired sample points. The two uses of McNemar's test. One is the binary classification problems when the outputs of the models are either positive or negatives. Here you have two classifiers and you want to compare their predictions. In paired samples, you have the same instance are classified by both classifiers so that predictions can be directly compared, and predictions from both models are made on the same data set. Multiple variables, aka multivariate linear regression. Now this is a statistical technique which is used to model the relationship between one dependent variable or two or more independent variables. It is an extension of linear regression where in this case multiple predictors are used instead of a single one to explain the variations in a target variable. The whole purpose is to predict or understand how the dependent variable changes with relation to the independent variables. Here we see the home prices in township of Monroe is calculated with respect to the size of the house, that is the area, the number of bedrooms in it, the age of the house. All these factors are combined into calculating the price of the house. Now the equation for multivariate regression is, here the price is equal to the M1 into area plus M2 into the bedrooms plus M3 into the age plus the intercept. Here the features are the independent variables which are multiplied with the coefficients, and the coefficients plus the intercept along with independent variables, all these are taken into account to calculate the price, which here is the dependent variable. This can be also be written as y is equal to m1 plus x1 plus m1 m2 into x2 plus m3 into x3 plus b. Here x1, x2, x3 are the independent variables which are the features. M1, M2 and M3 are the coefficients for the features respectively. Y is a dependent variable and B is the intercept. Here we have the code which explains the linear regression with multiple variables. This will be explained in further detail later. Logistic regression is a statistical algorithm that is used to estimate the probability of an outcome and classify the data points accordingly. Now it is classified into two types, either binary classification problem or multi-class classification. In binary classification, we have the outcomes that are either yes and no, and in multi-class classification, we can have multiple outcomes. Instead of predicting continuous values, it predicts the probabilities that maps to discrete classes. The basics of linear regression with multiple variables and logistic regression. Further in-depth explanation of the code and examples will be explained later. As of now, thank you.